To start off with, let's go right back to simple interest. Probably the first type of interest formula you would have seen. The idea is that you charge interest over the whole amount borrowed for the whole amount of time, regardless of how much you pay back. That's not fair. But as the name suggests, it's just a very simple idea. It's the first idea you look at to get a feel of how interest works. So if you had $3,000, let's turn it to the positive side. Let's make it an investment rather than borrowing. So $3,000 invested for 7 years, 6% simple interest. How much would it be worth after 7 years? So PRT, the amount we're investing, $3,000. The interest rate, I'm doing it as a decimal, so 6%, 0.06, times the 7 years. That's the interest. That's not the question though. The question is, how much is the investment now worth? So we add that back in, and it's 4,260. I think it's actually illegal for someone to offer you terms of simple interest, because if you do it the proper way with compound interest, which we'll have a look at. So compound interest, as it's often said, is interest on your interest. Once you've earned some interest, then interest gets paid on that, and you end up with more money, basically. Hence the compounding. But if you actually have a look at the formula for compound interest, the way I've written it anyway, it's quite familiar. And it is, in fact, a general term of a geometric series. So note that. Instead of A, I've got P, but it's instead of n minus 1, I've got n, but it's still that structure of a geometric series. So n time periods, principal. R in this case, though, is not just the interest rate, it's 1 plus the interest rate. Because this formula doesn't just work out the interest, it works the whole amount. It already adds it back in, so it's the amount you have plus the interest as well. And the key thing, of course, with all these formulas is we make sure that the time periods and the interest rate match up. So if they're saying compounds monthly, then my interest needs to be per month. Compound annually, interest rate needs to be per annum, and so on. So let's look at the same question. 7 years, 6% per annum. How much would it now be worth? Let's first of all assume it's compounded annually. So PR, the power of n, 3,000, 1.06 to the power of 7, and we get 4,510.89. What was it with simple interest? It was... So you see, we get a bit more by using compound interest. Now, if we compound monthly instead of annually, my interest rate's going to change. Instead of 6% per annum, it's now 0.5% per month, or 0.005. Instead of 7 time periods, because it's 7 years, we'll have 84 time periods, 84 months, and this time it compounds to, well, slightly more. What's that? About another $50 there. 4,561.11. If you ever get a choice, by the way, on the compounding, always go for the smaller time period, because the more frequently they apply the interest rate, the more money you're going to get. Depreciation, whilst we're talking about these formulas, well, it is exactly the same formula. But now depreciation is when it goes down. And again, this works out the final amount, this formula, not just the amount that's lost. So we take that into account with the R. This time the R will be the original amount, but minus, because it's depreciating, minus the depreciation rate. But exactly the same formula. So let's have a look at an example of that. An espresso machine. They tell me that's a coffee machine. I don't drink coffee myself. What, there's shock in the room? Bought for $15,000. So it must be one of those fancy ones that they have in the cafes and what have you. 1st of January 2001. Depreciates at 12.5% per annum. They want to know what will its value be on the 1st of January 2010. So that's after how many years? Be 9, wouldn't it? It's not 10. would it be? Hang on, you got all of 2001, all of 2002. Yeah, it's 9 years. So let's sub it in. And it's 1 minus the interest rate, so 0.875. So it's now worth about $4,500. $4,500. When or during which year will the value drop below 10% of the original cost? Well, it's just like our geometric series. It's an application of a geometric series. We want to know when is the general term below 1,500, which is 10% of the 15,000. So let's play around with that. Log both sides, bring the n to the front, divide, but remember, log of a number less than 1, it's actually a negative number I'm dividing by. So we change the sign. So when n is greater than 17.2, question is, during which year? Now we started on the 1st of January. So it'll be during the 18th year. So that would be 2018. That makes sense because the first year was 2001, the second year, yeah, so the 18th year would be 2018. It drops to 10%. So this is one of those ones where, even though it's 17.2, we don't round down because we're talking about greater than, we're always round up there. Where it becomes really useful is when we turn it into a proper geometric series. And so what they call, well, investing money by regular instalments. The best example is superannuation, where you're sort of compelled to these days put money into super, a certain amount at regular intervals. And well, this again is a very simplistic model where we're going to assume that the percentage return on our money is the same. Now, again, it's highly unlikely when you think about it, because a superannuation will go for many, many years. It'll start when you start working, keep going to when you retire. So what are you talking about, 30, 40 years? The chance of the percentage being exactly the same for all that, not going to happen. But as a simplified version, we can assume that. I suppose for projecting forward estimates, what they do though for the interest rate is to take an average. They go, okay, well look, it might have been 2% this particular year return, another year it might have been 8% return, and it fluctuates. Alright, let's have a look at this simplified version of superannuation. We're going to assume a constant rate here. Well, when we say we, it was the 2002 HSC. 8.75% is what we're saying as an average. That's not a bad return on your money, 8%, certainly these days. So $5,000 is the investment, but this is an unusual one. They're only going to invest once a year. So just at the beginning of each year, they're going to put in $5,000. Usually is more normal these days just to put in every pay period, so every fortnight, things like that. What's the value going to be when she does retire on the 31st of December 2023? Conveniently at exactly the end of a time period there, which makes life a bit easier for us for our calculations. So how many years are we talking about? Starts on the 1st of January, so it'll be all of 2003, 4, 5, and all of 2023, won't it? Yes, you're right, 21. Okay, so that very first amount that we're putting in, and it's compound interest, so that very first amount will be invested for 21 years. So that particular investment will grow to be whatever 5,000 times 1.0875 to the power of 21 is. But then the next year, we'll put another one in, but it'll only be in there for 20 years. But every one of these is just a term in a geometric series. So the next one, but it'll be in there for 19 years. And so on and so on and so on until we get to the very last one on the 1st of January 2023, and it'll just be in there for 1 year. What will my total investment be? Well, it'll be all of these terms, the sum to end terms of this particular series. And that's all superannuation is. It's just a geometric series that we're adding up. Now, I don't know how this was explained to you last year or not, or whether they just gave you a formula to sub into. I personally prefer to think of it as, oh, it's just a geometric series. And I already know the formulas for geometric series. So amount will be that particular series, the addition of all those. Okay, well, the first term, I'm reading it backwards. I'm going to say the first term is power of 1. The ratio is 1.0875. The number of terms we've got is 21. So what we're saying is the sum to 21. Let's put it into the sum formula. Bit of calculator work. And there's our total investment. Putting in $5,000 each year for 21 years. I've put an asterisk here because this wasn't actually one of the questions in the HSC that year, but I thought it was a nice example. We want to know, when does it first exceed $200,000? So all right, again, there's our series. The difference this time is I don't know what the last term is, because I'm going to try to work out how many years it will take me to get to 200,000. So it's N I want to find with this one. But other than that, it's exactly the same. We're now saying, well, when is sum to N greater than 200,000? Okay, there's my sum to N formula. Greater than 200,000. Looks horrible, but at the end of the day, 5,000 times 1.0875 divided by 0.08, that's just a number. So if I divide both sides by that number, and it turns out, and actually not quite neatly, the right hand side becomes 280 on 87. Alright, move 1 to the other side. Again, we've got an exponential one to do. Let's log both sides. Bring the n to the front. Divide, but it's a number bigger than 1, so the sign will change the same. Did I just say the sign will change the same? The sign will stay the same. Log divided by log. 17.1 years. So, what did the question say? Was it after how many years or?
Exceed.
Well, yeah, because it said after how many years, even though it's 17.1, at 17 years it hasn't exceeded it. When we get to the 18th year, it will have. Now, in reality, when we said 17.1, it's probably going to be very early on in that year. But the question they've said is, okay, after how many years? So 2021 will be the first time. And another interesting variation on the problem, $1 million. Everyone wants to know, okay, how can I get $1 million? Now, obviously, I don't want to be working forever. Let's say I'm going to plan to retire 31st of December 2020. That's a very short working life. Bit unrealistic, I suppose, unless you win lotto or something like that. But okay, when will this produce $1 million for me? So it's still the same series, but this time I don't know how much I'm investing. That's what I want to work out, how much I'm investing. Still the same geometric series though. So we're now saying, when is the sum to 18, because we only want to work 18 years, wouldn't that be lovely? When's that equal to $1 million? How many years have I got to work to get the $1 million? Sub into our formula. Now we want to make P the subject. So again, look, it looks nasty, but it's just a number, whatever that turns out to be. So I'll divide by that, or invert and multiply. There's my P. Better calculator work. So every year I would have to invest almost $23,000. That's which probably explains why people don't retire after 18 years. We keep going. So, alright, if it was possible, if my pay packet was good enough, I could invest $23,000 every year. The other time where it's really useful is loan repayments. Now, until the internet came along and sucked the fun out of this, I actually used to do this when I was working out, I want to borrow some money, how much can I afford? I would actually create the geometric series because I'd usually know how much what I wanted to buy was worth. I'd say, I want to pay it off in so many years. And I'd look at the bank and say, well, what's the interest rate? So I could work out whether I could afford to do it or not. These days, you go on the internet, they've got these loan calculators. You just plug the number in and it works it out for you. But where's the fun in that? So let's see. So the amount owing after n time periods. What you've got to get your head around is a loan is an investment. It's a reverse investment. So At any point in time, the amount owing is what I'm interested in. And so it'll always be the principal with the interest applied minus my investment. The repayments are an investment. So minus the instalments or the repayments with the interest applied. At any point in time we do that. So let's have a look at this example. Richard and Kathy are going to borrow $20,000 to go on overseas holiday. So I don't know, perhaps they're going to travel around Europe for a few months. Probably need a fair bit of money for that. The interest rate at this point in time is 12% per annum. Nice and convenient, 12, using that as a number, so I can do that per month. And oh look, compounded monthly. Oh, that makes life good. They start repaying the loan 1 month after taking it out, and the monthly instalments are $300. Okay. How much will they owe the bank at the end of 6 years? So we want to know amount 6. So the initial loan, the principal plus the interest, it's been in there for 6 years. I've borrowed the money for 6 years. So again, we use our geometric series, 20,000 in principal plus interest, so 1.01 to the power of 72. It's still the compound interest formula. So that's the first part of my equation. Now I've got to work out each of the instalments. This is what I'm saying. These repayments we're working out are actually an investment. So we treat them like an investment. We'll use the compound interest formula. The first repayment, which comes at the end of the first month, so it's like investing that for 71 months. The second repayment then will be invested for 70 months. And we'll keep going. The second last repayment will only be there for 1 month, because the last repayment, it's not going to be in there for any months, because once I've paid the last repayment, I'm not going to pay any interest. We're done. It's all paid off. So we think there's actually 2 investments happening here. The principal, the bank, is having an investment. It's investing in you. Because it's basically saying, I'm going to invest this money with you. How you spend it is up to you. Mind you, banks usually ask how you're going to spend it and make some sort of decision, but how you spend it's up to you. But I want you to give me this much interest on my investment. Whereas my repayments, I'm now investing in the bank. And I'm going to give them money and say, hey, I want that same interest rate you're charging me. Once that balances and our investments are equal, the loan's paid off. That's the idea here. So once all my investments here equal the bank's investment, so principal plus interest minus instalments plus interest is equal to 0, it's paid off. Now in this case it won't be paid off because we've only been going for 6 years. So the question is, how much is left? Well, the principal, the bank's investment is 20,000, 1.01 to the power of 72. My investments will be this series here. So the second bit is a geometric series. So I can sub it into a geometric series formula. Again, bit of calculator work. And we can see, righto, there is still $9,500 owing on this loan. Right? That's the difference between their investment, the bank's investment, and my investment. So how much interest have they paid? Well, I've paid back over 72 months $300 a month. So I have given the bank $21,600. That's how much money I've given them. The loan was for $20,000. So I've reduced the loan by $10,000. But the difference, therefore, must be, hang on, it's saying here the amount owing is $9,529. So the interest, where is it? My total repayments, I've paid back $21,600. But I've only reduced the loan by $10,470. The difference between the two must be the interest I've paid. So in this case, what do we got? over those 6 years, I've paid $11,000 in interest for a $20,000 loan. One of the other things we like to do is say, sometimes we know how much we want to borrow, we know how long we want to take the loan out for, we know the interest rate. The question is, all right, how much am I going to pay you back each month? So here we go. Yog's going to borrow $30,000 to buy a car. Yog was actually a student I taught once. I thought it was a cool name, so I put it in there. Yog. He'll repay the loan in 5 years. He wants to pay it off in 5 years, 60 equal monthly instalments. Interest is 9% per annum, compounded each month. How much are our instalments going to be? The monthly instalment is M. That's what we're trying to work out. How much am I going to pay back? The bank is investing in me $30,000 with the interest rate applied, power of 60. First repayment will be in there for 59 months. Second one, 58 months. And so on and so on and so on until we get to that last repayment, which will be thanks very much, we're done. So in this case, we do want amount N to be zero. The loans is going to balance with the repayments. Their investment and my investment are going to equal. So amount 60, which we know is going to be zero, principal plus interest, the bank's investment, minus my investment, all those repayments. And we can again use our geometric series. Whoop. But as I say, we know that's going to equal zero. They're going to balance out. We just now have to make M the subject of all this. So we'll move that to the other side, divide, and we get repayments of $622.75 a month. What's another situation we could have? Trying to work out. So we know how much we can afford to pay back. We know the interest rate. We know how much we're going to borrow. We say, well, okay, given those conditions, how long will the loan be? This one comes from an HSC. Yes, you've got to admire the humour of the HSC examiners. Do you get it? Think about it. It's a council. Councils do a lot of building work. The name of the council is? Wheeler-barrow back. So you get the wheelbarrow and you wheel it back. Okay. You can imagine that particular year, the people who wrote the HSC, they would have been sitting back laughing. They would have, imagine they're imagining, every HSC student will be opening up the paper, having a good old chuckle, when in reality they probably just opened and went, wheelbarrow. Probably didn't get the joke. Okay, we're talking about a council, so it's going to borrow a large amount of money. What have we got there? 3 million, is it? Yeah. $3 million they're going to borrow. Interest rate's 12%. What else do we know? Going to make lump sums each year of $480,000. Okay. So, the first part of the question was to show A2 is this expression. Sorry, after 2 years, so not a long time, 2 years, the bank's investment, and then the first repayment will just be in there for 1 year, and the second repayment, so there's only 2 repayments in that time. So amount 2 will be the principal plus the interest, minus the instalments plus the interest. Now, here's the thing with your working out. They've said show that. So I think these actual words are very important when you're setting this one out. Because if you didn't put those words in reality, you're just pretty much writing down the answer that they gave you anyway. So by writing the words in, you're explaining, I know how you got this. And then we can rewrite it in scientific notation, which is what they've got it done, and we've got the answer. I'd probably write those words down anyway, regardless. Again, it's just part of my solution, so I'm just letting them know this is the approach I'm taking. Bank's investment minus my investment, the repayments. Right, we want a general formula now for the amount owing it. So initial loan borrowed for N years. First repayment will then be N minus 1, whatever N is. then n minus 2, and so on and so on and so on. We get to that last repayments. Principal plus interest minus instalments plus interest. Subbing in, we need to show this expression up the top. Well, we're going to need to use our sum to end terms for the part over here. So first term 480,000. Whoop, sub it in. Now, amazingly, something really nice happens here. 480,000 divided by 0.12. Oh, what do you know? That's just 4 million. Now, the way they wrote it, they had a number times 1.12 to the power of n. So I'm going to have to expand this out. And I can say, well, I've got 3 million minus 4 million, so that would be negative 1 million all up. And I get the expression that they wanted. Well, factorise out the million or the 10 to the power of 6, and we get there. So the next part of the HSC question was then something they logically would want to know. Well, when are they going to make that final repayment? So when is the amount equal to 0? We've just worked out a neat little formula, so we may as well use it. And just got to make n the subject, move the 4. Once again, we've got an exponential equation. Log both sides, divide. 12.23, they've said which year, so it'll be the 13th repayment, which will happen at the end of 2017. Oh, they've almost paid it off. End of this year, they'll have it done. Alrighty. There's 3 different exercises there. I've just picked 4 out of each. I think you'll find the first one is just the simple interest and compound interest. The second one are all superannuation problems. And the third one are all the investment problems, the time payments and what have you.